Ever wondered how a simple chemical reaction can lead to the creation of life-saving drugs? It all starts with the magic of unit processes in chemical synthesis. These processes are the backbone of the pharmaceutical industry, transforming raw materials into the active ingredients that make our medicines effective. Whether it's aspirin for your headache or antibiotics to fight infections, unit processes play a pivotal role in their creation. These unit processes are a series of fundamental chemical reactions, including the likes of nitration, amination by reduction, esterification, hydrolysis, oxidation, and alkylation. Each of these processes, in isolation, may not mean much, but when combined in a specific sequence, they hold the power to synthesize complex molecules that can combat diseases and enhance human health. Today, we'll be demystifying 6 such unit processes: nitration, amination by reduction, esterification, hydrolysis, oxidation, and alkylation. So buckle up for an insightful journey into the intricate world of pharmaceutical synthesis. Starting off with nitration, a critical process in the formation of many pharmaceuticals. Nitration, at its core, is the introduction of a nitro group into an organic compound. The nitro group, consisting of 1 nitrogen atom and 2 oxygen atoms, is a fundamental building block in the formation of many drugs. But how does this process happen? Well, it all starts with nitric acid, a potent and reactive substance. Nitric acid acts as a nitrating agent, facilitating the insertion of the nitro group into the molecule. It's a bit like a matchmaker, introducing the nitro group to the organic compound and helping them bond. This bond formation allows for the creation of a variety of complex structures that are vital in pharmaceutical synthesis. Take paracetamol, a common pain reliever and fever reducer, as an example. The nitration of phenol, a precursor in the synthesis of paracetamol, is an essential step in the production of this widely used medication. Without nitration, the synthesis of paracetamol would not be possible. Nitration isn't just important for paracetamol, though. It's a key process in the synthesis of numerous other active pharmaceutical ingredients, APIs, including certain antibiotics and antimalarial drugs. It's a powerful tool in the chemist's arsenal, enabling the creation of a vast array of life-saving medications. Nitration, therefore, plays an integral role in pharmaceutical synthesis. Next up, let's delve into the world of amination by reduction. This fascinating process is a cornerstone in organic chemistry, playing a pivotal role in synthesizing a broad range of compounds. Amination by reduction involves the addition of an amine group to a molecule. Now, what's an amine group, you ask? It's simply a nitrogen atom bonded to hydrogen atoms. This process is crucial because it helps transform simple molecules into more complex ones, expanding the spectrum of potential pharmaceutical compounds. One key aspect of amination by reduction is its role in reducing compounds. Reduction in chemical terms is the gain of electrons. So in the amination process, the molecule we're working with gains electrons, hence becoming reduced. Now, how does all of this tie into the synthesis of active pharmaceutical ingredients, or APIs? Let's consider ephedrine, a potent medication used to treat a variety of conditions. Ephedrine is synthesized through amination by reduction, where the starting material, often a simple molecule, is transformed into a more complex one. This transformation aids in enhancing the therapeutic potential of the original molecule, making it more effective in treating diseases. So you see, amination by reduction is not just a fancy phrase. It's an intricate process that plays a significant part in the creation of life-saving drugs. Amination by reduction, indeed, is a cornerstone in creating effective medications. Moving on to esterification, a process that is as interesting as it sounds. This chemical reaction involves the synthesis of esters from carboxylic acids and alcohols in the presence of a strong acid. The result is a sweet-smelling compound, hence why esters are often found in perfumes and flavorings. But that's not all. In the pharmaceutical industry, esterification plays a crucial role. The creation of ester compounds is a stepping stone in the production of a variety of active pharmaceutical ingredients, or APIs. One of the most well-known examples is aspirin, or acetylsalicylic acid. So how does this happen? Well, in its basic form, aspirin is created by the esterification of salicylic acid with acetic anhydride. The acetic anhydride acts as the acetylating agent, while the salicylic acid provides the phenolic hydroxyl group. This reaction results in the formation of an ester group, giving us the medicine we know and use today. The beauty of esterification lies in its simplicity and versatility. It's this very process that enables the synthesis of complex APIs from simple, readily available starting materials. So whether it's a headache remedy or a life-saving drug, esterification plays a key part in its production. In essence, esterification is fundamental in the production of many common drugs. Now we dive into hydrolysis, a process crucial for breaking bonds. The term hydrolysis might sound a bit complicated, but it's really just a chemical reaction involving water. The word itself comes from hydro, meaning water, and lysis, which means to separate. So what does hydrolysis do? It breaks down compounds by inserting a water molecule into them. This can result in the breaking of ester or amide bonds, which are common in many pharmaceutical compounds. This is particularly important in the synthesis of active pharmaceutical ingredients, or APIs, as these bonds often need to be broken down and reformed to create the desired product. Take penicillin, for instance, a life-saving antibiotic that has saved countless lives since its discovery. The key step in its synthesis involves a hydrolysis reaction. The penicillin molecule contains a three-membered ring structure, which is unstable and prone to opening up. By using hydrolysis, we can break this ring open, creating a more stable and, importantly, more effective antibiotic. But it's not just penicillin. Many other APIs also rely on hydrolysis for their synthesis, making it a critical part of pharmaceutical manufacturing. So when you take your next pill, remember the essential role that water, the most basic of all molecules, played in its creation. Hydrolysis, therefore, is a key process in the deconstruction and reconstruction of many APIs. Finally, we explore oxidation and alkylation, two processes with big roles in pharmaceutical synthesis. Let's start with oxidation, a process that involves the addition of oxygen or the removal of hydrogen. This process can dramatically change the functionality of a molecule, making it a key player in pharmaceutical synthesis. Take the synthesis of cortisone, for instance. Cortisone, a steroid hormone, is used to treat a variety of conditions, from skin diseases to autoimmune disorders. During its synthesis, oxidation plays a crucial role in transforming the precursor molecule into the final product. It's through oxidation that the molecule acquires the necessary oxygen atoms, forming the characteristic structure of cortisone. Now, let's turn our attention to alkylation. What is it? Simply put, alkylation is the transfer of an alkyl group from one molecule to another. This process, like oxidation, can significantly alter the properties and functionality of a molecule. Consider tamoxifen, a medication used in the treatment of breast cancer. The synthesis of tamoxifen involves an alkylation step, where an alkyl group is transferred to the precursor molecule. This transfer is what gives tamoxifen its unique structure, which allows it to bind to estrogen receptors and inhibit their activity. In other words, it's thanks to alkylation that tamoxifen can perform its life-saving function. So why are these processes important? Well, they allow chemists to manipulate the structures of molecules, thereby creating a wide array of active pharmaceutical ingredients, or APIs. By using oxidation and alkylation, chemists can engineer molecules to interact with specific biological targets, leading to the development of effective treatments for a variety of diseases. Oxidation and alkylation in many ways are the finishing touches in the creation of a variety of APIs. These processes, though seemingly simple, hold the power to transform a simple molecule into a potent medication, proving once again that in the world of pharmaceutical synthesis, every step counts. So there you have it, 6 critical unit processes in the synthesis of APIs. We dive deep into the nuances of nitration, the process that introduces nitro groups into compounds, a key step in creating effective pharmaceuticals. We explored amination by reduction, a vital process for introducing amino groups, integral in many drugs. We also highlighted esterification, the reaction between carboxylic acids and alcohols that forms esters, often used in prodrugs. We discussed hydrolysis, the breaking of bonds with the addition of water, a fundamental process in drug metabolism. Finally, we delved into the intricacies of oxidation and alkylation, 2 processes that modify organic molecules to enhance their pharmaceutical potency. Each of these unit processes is like a unique piece of a puzzle, bringing us one step closer to the final effective API. Subscribe for more because you won't find me later. we'll continue to unravel the fascinating world of pharmaceutical synthesis.